Okay, so if you're not all the way done, that's totally fine. We don't need to be running code examples right from the get-go. So when we get to that part, if you're stuck, I'll be able to come around and sort of help you individually. But just so you know who I am, my name is Jane. I'm a data scientist. I work at Two Sigma Investments down in like Chinatown. And I also am the co-author and co-maintainer of a Python unit testing library myself. So I love unit testing a lot. I am a data scientist by training, but I do wind up writing a lot of software. And probably like many of you, I, in my sort of early career, a bunch of engineers, I would always hear engineers saying things like, oh my god, like data scientists, they never test their code, they never test their code. Why don't they test their code? And, you know, as a data scientist who now tests a lot of her code, all of her code, I am really interested in like what this disconnect between like software engineers and their idea of unit testing and data scientists and our idea of testing and like how to bridge that gap. So what we're going to sort of go through today is we're going to talk about unit testing at a pretty introductory level. We're going to talk about what a unit test is. We're going to talk about why we want to unit test. We're also going to talk about how to write unit tests in the traditional form where you're testing like an actual Python package, but also what can you do if most of your work is being done in a Jupyter notebook. So it's not super easy to extend unit testing to a Jupyter-driven workflow, but there are some things that you can do, so we're going to sort of talk through those. This is going to be really interactive. You're going to be writing a lot of tests for the next couple of hours. The only way to get good at unit testing is to practice a lot. It's really uncomfortable when you first get started. It's painful. You don't know what tests to pick. You don't know how to write them. You don't know how to run them. So we're going to get hopefully as much of that like pain out of the way together today as we can. So just to level set, who in the room has actually written unit tests before? That's okay. That's totally fine. I wrote my first unit tests in a tool that doesn't even exist anymore, which makes it seem like I wrote them a really, really long time ago, but that's actually not true. I didn't write my first unit test until I was out of grad school, so 4 years ago. Okay, so let's get started. So let's say, I want you to sort of consider these 4 functions that I've written, right? They seem pretty straightforward. The first one returns true for even numbers, the second one returns true for odd numbers, the third one returns true for composite numbers, and the fourth returns true for prime numbers. And what I want you to ask yourself is, like, these look really straightforward. They look like the code is correct, but how would you actually go about determining whether or not these work? That these are doing what you think they're doing? What might you do?
Try edge cases.
Cool, like what?
Like, I was plugging like 0 or something very large, you know, since you're doing like odds and evens, it's not really an edge case there, but like, you know, you try and pick like extremes that aren't like maybe 90% of your expected use case.
Yeah, totally. So you just described what a unit test is. Like, that's all it is. Cool. Unit test is the process of taking a predetermined, like a set of inputs and a set of known outputs, and making sure that when you provide those inputs, you get those outputs. Like, that's all unit testing is. And so what, so you said we could pass edge cases to these functions. We could do that, but also why just edge cases? Like, we could also pass, like, sort of maybe inputs that we expect a lot of users to provide, for example. But I'm glad that you brought up edge cases, because we're going to get to why that's important later. So unit testing is like, it's just like a dead simple you know, if I give this input, make sure that I get this output back. Like, that's all there is to it. The hard parts of unit testing are, you know, reasoning about, these are really, really easy examples, like example functions. The more complex your code gets, reasoning about what, you know, pairs of inputs and known outputs you can test with becomes a lot more challenging. So what does it look like? Or I'm sort of going to go more into the definition of a unit test, what it is and what it isn't, and then we're going to see an example of it. So the unit in unit test refers to the code that's actually under test, and it's called a unit because a unit is supposed to be something that's indivisible. So we want to test the smallest bits of our code as we can with our unit tests. And the reason we want to do this is that we want to isolate all of our tests from one another so that their failures are it's very easy to tell when a unit test is failing what part of the code is broken or what part of the code needs to get fixed. And so if we can write, you know, if we have one big unit test that tested like a whole bunch of different things, when that fails, it's that much harder for us to go back into our code and figure out what we need to change. And so if we can sort of split our code out into this isolation, we get it through two different ways. One is that we separate our code into really, really small components, right? So those 4 distinct functions, as opposed to one function that would like take an input and like spit out even or odd or composite or prime or something like that. Split it out into separate things, and then we have separate tests that test each of those things separately. So I know that if my is even test is failing, but my is odd test is passing, that I probably don't need to go look at my is odd. I know that the problem is definitely in my is even function. The test part of unit test is just the verification that the code under test is working. So a unit test cannot prove that your code is correct. This is a pretty common misconception with unit testing. But what it can do is it can say, you can use unit tests to say, okay, does my code perform correctly against a given set of like formal requirements? So you have to say what you expect the behavior to be. And if all your tests are passing, you can say, yep, your code works in all of those cases that you enumerated, but you're never going to have like an exhaustive set of, you know, possible conditions that your code could be running in or possible inputs that people are going to be passing to your code. Another thing that's sort of implied when we're talking about unit testing is that unit tests generally refer to automated tests. So these are tests that are run by a machine rather than tests that are run manually by a human. So we could pop open a terminal or a Jupyter notebook and we could pass the edge cases that were mentioned earlier and look at the outputs. We could sort of manually test it that way. But having a machine run your tests for you in an automated fashion is a lot better for like a couple of reasons. First is that automated tests are faster. It's a lot faster for a machine to execute your code or sort of iterate over a set of inputs and outputs than it is for you to iterate over those inputs and outputs. They're also, they're more consistent. The reason they're more consistent is that if you're trying to manually test for something, you have to remember how you tested for it the last time you looked at it. And if it's been weeks or if it's been months, you know, that's going to be pretty challenging. You can test for more things. This is related to the fact that automated tests are faster, and also the point below this, which is that automated tests are easier to maintain. Because you can test faster and because it's easier to keep track of your expectations that you're trying to test when you put it in code, you can wind up testing for a lot more things than you can afford to test for if you're doing manual testing. And then finally, automated tests are a lot easier to maintain than manual tests. You know, if you wanted to maintain your manual tests, you would be looking at writing, you know, like a testing manual and training people how to manually test, and like all that takes a considerable amount of work. Okay, does anybody have any questions so far?
try to enumerate all possible cases?
So that's a good question. So the answer is no. One, because that's impossible. And two, because it takes time to write unit tests. It takes time to write the code. It takes time to think through the design of the test. It takes time for people to review it if you're in an environment where code reviews are required for code changes and things like that. And so you have to do a cost-benefit analysis when you're looking at what tests am I going to implement. And for for a lot of those cases, like sure they might possibly happen, but either they're super, super rare, or they wouldn't be that big of a deal if it happened. You sort of get diminishing, you don't get a lot of value out of spending time writing that unit test. So we're going to talk kind of in the middle of our time together today. We're going to talk about how do you do what's called test planning. And test planning is the process of figuring out what tests you want to write and what tests you need to write. Okay, so just a quick note that I use, there are a couple of different Python libraries for writing unit tests. I prefer the built-in library, which is called unit test. Probably the most popular testing library is called PyTest. Who in here has heard of PyTest and not of unit test? Nobody? So it doesn't matter what library you use, as long as you're writing tests. If you want to use PyTest, you definitely have my blessing. But unit test is the one that I'm really familiar with. And I prefer it for a lot of reasons that if you want to get into it with me, we can fight about it later, but you really shouldn't get involved in the PyTest unit test wars this early on. So just so you know, when you're looking at this repository, you're looking at these examples, these are all using unit test. So I wrote the following unit tests for our four functions. So I'm going to sort of walk you through what's happening here. So the first thing that I do is I import my Python. Yep. Oh. Sorry. That's okay. There's so few of us that I feel like I should have asked people's names. But, okay. So the first thing I do is that I saved those four functions into a Python module called nums.py. I didn't name it numbers because there's a numbers module in Python, and it's just generally a good idea not to name things the same as things that already exist. So the first thing that we have to do is we need to import it so that we can test the functions that are defined in it. And the second is I need to import unit test because unit test, this module provides the resources that I need in order to actually write my unit tests. In Python's unit test, wow, it's going to be really difficult for you to distinguish when I'm referring to unit test as a concept and unit test to the library. So I will try very hard to say Python's unit test when I'm referring to the library. So in Python unit tests are organized into test cases, which are classes. So if you've never seen a Python class before, you've never worked with a Python class before, this might be pretty scary. We're not going to get into Python classes really at all in this session. This is not what this session is about. So the short story is that a test case is a Python class with a bunch of test methods on it. And each method is this block of code that looks exactly like a function. Right? So a method is almost identical to a function. It's just a function that's attached to a class of some kind. So we organize our unit tests into test cases like this. In this case, we only have one test case, and we put all of our test methods on this single test case. And when you're first starting out and when your projects are small, it's totally fine to just have one test case. If your projects are getting bigger and they're getting more complicated, then you might want to create multiple different test cases and sort of split your test methods across multiple test cases just to keep things organized, and so it's clear to you where are my tests for this feature and where are my tests for that feature. But when you're first starting out, you're probably just going to have one test case, and that's totally fine. And then finally, at the end, we have this, this little block. And what this block does is it allows us to say, if we just run this script from the command line, if we just say Python test nums.py, this will trigger unit tests to actually load and run each of these tests. So I want you to ignore everything but this. One of people's biggest complaints about Python's unit test is that it has a lot of boilerplate, and the boilerplate that they're talking about is everything that's not highlighted, which I don't think is a huge deal. I don't think that's a lot of boilerplate, but some people really find it cumbersome. So each of these methods is an individual unit test. And every single unit test, whether you're working in Python's unit test, whether you're working in PyTest, whether you're working in Marbles, which is the library that I'm the maintainer of, a unit test has two basic steps. The first is that the code under test, the code being tested, is invoked in some way. And the second is that an assertion is made. So in this first example, this is where we're invoking the code. We're invoking our isEven function with the input parameter 2. And the assertion that we're making is that that's true. We're asserting that when we invoke that code with the input 2, the true is returned to us. And so, sort of moving through these test cases. Of course, when we pass 3 to our isEven function, we want to get false back because 3 is not even, and so on and so forth. So, in unit test, assertions are made by using these assert methods on the test case. And there are a bunch of different, I'm only using assert true and assert false here, but there are a bunch of different assert methods in the unit test library that you can use. There are things like assert is none, or assert that two lists are equal. They have quite a few number of assert methods that are actually pretty semantically rich. You can probably get away with using just assert true and just assert false if you want.
Looks like false and true, are they coming from the unit test library?
They are coming from the unit test library. So they, so see how we've defined these methods on our nums test case class? So because we inherit from, this class is inheriting from unit test case, assert true and assert false are just methods that are defined on our superclass. So that's how we have access to them. And so this is how you make assertions using Python unit test. And there's a link in these docs to all of the assert methods that are available. In PyTest, assertions are made using just like the bare assert keyword in Python. So our is prime test from above would look like this in PyTest. So in PyTest, it would simply be a function. And there's no sort of that pesky self that comes from Python's object orientation is not hanging around. So in either framework, either Python's unit test or PyTest, if the assertion fails, it's going to raise an exception called an assertion error. And the test will fail. If it encounters another exception while it's trying to execute your test, the test is going to error. And then finally, if no exceptions are raised, your test is going to pass. So failures and errors are, they're different from one another. A failure indicates that the asserted condition did not hold, while an error indicates, okay, something went wrong while I was trying to run the test and I wasn't actually able to like evaluate the assertion and I don't really know what happened. And so we're going to see, we're going to run our tests that we wrote, that I wrote. We're going to run the test that I wrote, and we're going to sort of see what the unit test results look like. So I think we can get away with doing this even if you don't have requirements installed, but you just have the repository. Okay, so what I want everyone to do is to go into the top level of their clone. Is this big enough, by the way? So okay, so I want you to cd into this directory. Welcome. Sort of, if you want to look at what's inside, there should be two files. There should be our nums.py file and our test nums file. Who's there? Cool. Okay. So we want to run our tests. And all we have to do is pass that file to the Python interpreter. Dang it, I wanted this to fail. Aha. Hold on while I break my code. Okay. Okay, there we go. So, what we're seeing when we look at this output is we're seeing that we ran 4 tests, right? So we had written 4 tests. It took 0.001 seconds to run those. That's pretty fast. And we can see that 2 of our tests errored. That's what the 2 E's up here mean. And we can see that 2 of our tests passed. So the 2 dots are passes. So I broke my code intentionally so that we could see these errors. But for any errored or failed test, you will get a traceback that looks like this. And so what we can see is we're running into, we can see the test method that failed, and we can also see what the exception that was raised, like the non-assertion error exception that was raised while trying to run this test. And what we're getting is a 0 division error, integer division or modulo by 0, which makes sense, we can't divide anything by 0. And so I have some code to fix. So let me go fix my code. So the way I'm going to fix my code, this is sort of not super relevant to you all. This is not a class on composite prime numbers, but I was iterating over a range that included 0 and trying to divide my number by 0, and so that wasn't going to work. So I added some logic to make sure that we iterate from 2 to whatever my number is. And it also turns out that 0 and 1 are neither prime nor composite. So in both of these functions, if n is less than 2, we just return false. And so now if I run my tests, all 4 of them run, and all 4 of them pass. So Were all of you able to run that file and get the 4 tests to run and all of them to pass? Was it exciting? Not even a little bit? Okay, fine.
It's always organized this way. You have a library of some classes and then a test library instead of a separate file.
So that is another good question that we're going to get to later, which is sort of where do you put your test code? It depends on how big your project is my short answer. Okay, so we just went over this. I wrote my code to get these errors. I fixed them, and then I run my tests again, and all of them pass. And so you can see why this might be useful, right? Yeah, okay, good. Moving on. So in our sort of second hour together, we're going to dig more into actually writing unit tests, and you're going to get practice like actually writing unit tests. But before we get there, I want to talk about why you should be writing unit tests. And I'm going to talk to you about why software engineers write unit tests, and we're going to talk through the reasons that they, we're going to talk about the motivations that they use for writing unit tests. And then I want to talk about why you all specifically should be writing unit tests. And I want us to all understand the motivation before we sort of keep doing this like slightly weird, slightly uncomfortable exercise. Because if you know why you're doing it, you're going to stick with it. And if you don't understand why you're doing it, you're never going to pick up the habit. So the first one is one that we already know. We want to write unit tests to ensure that our code works under a given set of conditions and for some definition of works, right? We can't prove that our code is working 100% correctly. Like they don't guarantee that it will work under all conditions, like for all inputs. And that's not even the goal of unit testing, as you kind of passed. The goal is to get like a reasonably complete set of conditions covered, and to make sure that your important bases are covered, your important concerns are covered. And so having unit tests in place can help you catch a whole bunch of different kinds of errors in your code. It can help catch exceptions that you didn't know were getting raised, like I saw with the zero division error. It can help you catch syntax errors. It can also help you catch like problems in your math if you have code that's performing pretty complicated math. And there was this, and if like that doesn't convince you, there was this like amazing study published in Usenik's OSDI in 2014 that concluded that like 58% of catastrophic failures across 200 different distributed systems could have been prevented with just like basic test coverage. So not exhaustive, just like basic. If there had been just some simple tests in place, some of these catastrophic failures could have been avoided. So I don't know if you all are writing code that could ever experience a catastrophic failure, but a lot of the code out there that gets, probably most of the code out there that gets written can't actually cause a catastrophic failure, but I work on code that could cause some catastrophic failures. Another one, this is probably more relevant to you, is detecting what are called regressions. So a regression is when code that was previously working stops working for some reason. And having unit tests in place is incredibly helpful for detecting regressions, especially when you're doing things like refactoring your code. So refactoring your code means that you're making changes to the code that don't affect like the surface level API. So like you're not changing the name of functions, or you're not changing the functions that are available. You're just like changing the internals of a function that already exists. Maybe to make it faster, maybe to make it simpler, but the functions should still provide the same inputs and outputs. And so sometimes while you're refactoring, while you're changing code, every time you're changing code, there's a possibility that you're breaking something that used to be working. And so sometimes the code that you break is the code that you're working on, but sometimes the code that you break could be like completely elsewhere in your code base and you're not even really thinking about it. And so even if you're good about manually testing that the code you're working on, like the code you're actually changing, is still working the way you think it's working. It's really, really hard to remember, okay, what are all the other parts in my code base that might be affected by this change that I just made? And so having unit tests in place that you can really, really easily run is a really great way to make sure that changes that you're making to the code aren't introducing regressions elsewhere in your code base. Another really, this sort of last paragraph here probably should have been its own section because it's very important. But the other place where unit tests come in handy is, and to put it lightly, is when you need to upgrade packages. Or, for example, if you need to upgrade versions of Python. So Python 2 is end of life. Many, many packages are dropping support for Python 3. The only way to safely upgrade a package is to start with a well-tested code base. And by safe, I mean without the possibility of breaking something. And so when you upgrade a package, unless you're sort of very careful about like reading the change log for like the version, which nobody does that. It's really hard to read through all the change logs to figure out like, is this going to break me in some way? Is this going to introduce the change that I need to deal with? When you upgrade a package, sometimes it can break your code in a really, really loud way, where if you try to run your code now, it errors out, and exceptions, it like yells and screams at you. The more concerning case is when you upgrade a package and it doesn't break, it just starts to give you slightly different results. But like nothing is erroring, and so like there's no alarm bells going off that there's something wrong, but you're getting different results than you were getting when you were using a previous version of that package. Another one of the huge value adds of writing unit tests is that it forces you to sort of think through the failure modes and edge cases of your code. We spend a lot of time, probably most of our time, thinking about how our code is going to work. Spend a lot of time trying to get it to work. But thinking through how it's going to fail is a good way. You often can identify sort of logical errors in your program, and it can also help you identify edge cases that need to be handled specially. So in our example, 0 and 1 are neither prime nor composite numbers. So when I got that 0 division error, I was like, is 0 a prime number or is 0 a composite number? Then I went and looked it up and I was like, oh, it's neither. I need to handle that specifically in my code. And so after I add that special handling, which I realized I needed because I was unit testing and I was thinking through the ways that my code was going to fail, it's a really good idea to add additional unit tests for those specific edge cases. So I warned you that we were going to do a lot of practice. If you all could open our test nums file in whatever editor you like. This is how I shouldn't have given you the answer. This is how I tested for 0 and 1. I just added sort of 2 new test methods by myself. If you want to test it a different way, feel free, and then tell us all about it. But what I want you to do is I want you to add these test methods to that file and run the tests to make sure that they pass. How'd you do? Was anyone able to run them? 6 passes? Cool. 6 passes?
The other way is the only one I can think of is like true function.
So that's one way of doing it. I guess like the other way, we don't need to make this more complicated than it is. The other way would just be to put, instead of having 2 separate test methods for 0 and 1, we could add each of these assert methods to our tests for each of these functions. So what that would look like would be like the reason I didn't do that, and the reason I put them in separate test methods, is that I like, we'll get into sort of what makes a good unit test later on in the seminar, but generally you want each of your unit tests to be focused on doing one thing. And I kind of like to split edge cases out into their own test methods. I can name them, I can give them special names that indicate to me that like this is a special case, this is the special case that I'm testing for, and sort of splitting edge cases out from the happy path or like the sort of expected, the sort of normal behavior. Okay, so the very practice of writing unit tests puts you in this sort of adversarial mode where you're thinking about not how your code is going to work, but how your code is going to fail. And doing that up front can help you realize logical errors, edge cases that you didn't consider before, and that can save you a lot of headaches down the line, like thinking about them up front. So the last one that you'll hear people talk about is that unit testing helps you write better code. And what they mean when they say that is that well-factored, loosely coupled code is easier to test. And I'm going to say what both of those things mean. But basically the idea is because well-factored and loosely coupled code is easier to test, unit testing incentivizes us to write code that's well-factored and loosely coupled. And so it's an example of making the right thing to do the easy thing to do. And so that's what people mean when they say that unit testing helps you write better code. So what factoring is, factoring refers to how you have broken your code up into individual components. So how you've broken your code up into individual functions, what classes you've decided to create with what methods. So generally, smaller, more single-purpose pieces of code are a lot easier to test than larger pieces of code that do a whole number of things. Loosely coupled means that your code doesn't rely on the internals of sort of any other code or any other system. So it's very easy to get at your code sort of just by itself. The really classic example here is if you have code that connects to a database. So testing that code can be very difficult. For instance, like what do you do if the database is down? You wouldn't want your test to fail in that scenario because there's not anything really wrong with your code. Like the problem is that the database is down, but like your code is still working correctly. And so code that makes it easy for you to sort of like separate your code from the sort of external services that it depends on winds up being a lot easier to test. So the sort of last part I promised, why should everyone in this room write unit tests? And then we'll take like a short 5-minute break. We're together for like 3 hours, so I want to try to get 2 breaks in just so we're not like falling asleep. So as I said when we first got started, if you're a data scientist or a researcher, which term do you all actually prefer? Or how do you identify? Researcher? Okay. I don't actually really identify as a data scientist, but that's like my title. But I'm just like a data practitioner. Okay, I'm in a room full of researchers. So, and how many of you have heard like someone be like, oh, like researchers never test their code? Nobody? Okay, you work with very, very kind people. All I would get were complaints whenever I wasn't writing unit tests. I was like, oh, you freaking like data people, you freaking like scientists. So this is a sentiment that people have, and a lot of engineers will say things like, researchers and data scientists really need to be testing their code. And I want to dig into a little bit about what they're actually trying to say when they say that. So one of the reasons that data scientists and researchers don't write unit tests is that the code that we write is often stochastic. And it doesn't produce the same result every time we run it. And so unit testing kind of assumes that there's like one known result that like you can test for. And so mapping that onto stochastic programs is like a little bit awkward, but we're gonna, at the very end, we're gonna talk through how we might go about testing stochastic programs. And another reason is that a lot of the time we're working in Jupyter notebooks instead of in standalone, instead of in like Python packages. And we also don't really have users. I mean, you all might have a different experience. I would be interested to hear. You're usually the primary users of your own code, right? Yeah. So, so why should you be writing unit tests if it's harder for you and the value add is like only for you personally and like not for your users that are sort of depending on you, or like you're managing your own code? Like, why does it matter? So one that still applies to you is safely upgrading packages. If you're working, depending on the context that you're in, if you work with engineers, if you collaborate with engineers, they may be responsible for maintaining your development environment. It depends on how strict of an environment you're working in. The environment that I work in is pretty darn strict. I don't have a lot of control over my own development environment, and I actually prefer it that way. And so at times, they need to upgrade packages for security reasons. They need to patch a security hole or whatever. And again, as we already said, the only way to safely upgrade packages is to start with a well-tested code base. So they don't want to upgrade a package, so they've got to upgrade a package. They don't know if they're going to break your stuff, and everyone gets like upset. The other big one is avoiding this very sad beached whale. I guess it's a dolphin. Like, it worked on my machine. Sometimes you'll be working on something on your local machine, you'll be developing it, it gets to a good enough state, and then you hand it off to someone else to put into production. Or do you all have do you have a version of this? Yeah. So what production generally means, it's a super loaded term. Almost everywhere you go, everyone means something different by it. But generally, it's being deployed and run on a machine that is not your own anymore. And the person that's responsible for moving your code into production wants to have some assurances that they didn't break anything while they were moving it, right? So like if it gets deployed to production and then the first time it's run, it breaks, like you're going to be really upset. The person that moved it is going to feel really bad. Nobody's going to be really happy, and everyone's going to have to fix it. But again, we also have this problem of, that's the good case, like when it fails really loudly and it breaks and like people know that something's wrong. The scarier case is when it's deployed and it doesn't like explicitly break, but all of a sudden your model is returning slightly different results than the one that you prototyped in your own local environment. That's not a good situation. Which brings us to kind of the most important one to me, which is that unit tests help me isolate changes in my results to changes in my input data or changes in my model. So I want to make sure that when I change my input data or when I change my model, that those are translating into sort of like legitimate results. And I'm not getting different results simply because my code is doing something that I don't think it's doing or that I don't know it's doing. So having unit tests in place, trying to really, really, really robustly test all of the pieces of my code around getting my model set up and getting my model run, getting those really, really well tested, gives me more confidence that changes in my results are real. And finally, we sort of talked about this a little bit already when we were talking about factoring code. Unit tests sort of force you to break your code up into individual components, right? So it's very, very hard to test a function that does 10 different things because you need to test that each of those 10 different things happens. You probably need to test that it happens in the right order, which is really difficult to do. And so unit testing, it's gonna force you, you're gonna get sick of writing tests for these sort of overloaded functions, and you're gonna start just naturally writing smaller and smaller and smaller functions. And one big advantage of that is the smaller they get, they're probably gonna become more sort of general purpose. So if you ever find yourself like copying the same cells from notebook to notebook to notebook, to sort of reuse the same logic, you know, that's a good indication that you might have some code that you can actually factor out into like a utility library for yourself. So what you can do is you can take that code out of the notebook, break it down into tiny, tiny, tiny pieces, test all those tiny, tiny pieces, and then import it into all of the Jupyter notebooks that you need to use it in, and you can be confident that it's going to work in every single one, because you put it in one place and you tested it in that one place. Okay, so we're going to pause for 5 minutes. Okay, we're not all back, but let's get started. So for the next hour, we're going to focus on writing unit tests, and I want to leave you all about half of the time to actually write some unit tests for your own code, whether that's code that's in a Python package or that's code, or whether that's code that's in a Jupyter notebook. So I'm going to talk for a little bit about how to test both, and then everyone's going to sort of work independently, and I can sort of walk around and sort of talk through things with each of you as you're working. So, as I already talked about, there are a couple of different libraries and frameworks for writing unit tests in Python. We already talked about the first two, which are unit test and PyTest. The third is Marbles, which is my project. There's also a project called Nose, and another one that's called Duck Test. So this is not an exhaustive list, but these are the ones that it's probably useful for you to know about as you sort of venture into unit testing. So we probably don't need to talk about unit testing more than we already have, but one of its big advantages is that it's built into the Python standard library. And it organizes test methods into classes, which can be alienating for people, but it is pretty easy to get the hang of it. So PyTest is a really, really popular testing library for Python. One of the things that PyTest users really like about it is that it doesn't have all of the boilerplate that you get with unit tests, because you don't have to write classes. My personal opinion is that boilerplate and that sort of strict structure actually makes the tests a lot easier to understand. And it makes it a lot easier to reason about what the tests are doing, which is an important thing to be able to do, because you don't want to get into a situation where you feel like you have to write tests for your tests. Marbles is, because I prefer unit test, it is based on unit test. It just extends unit test to provide sort of better, more information-rich failure messages. But writing Marbles tests is exactly like writing Python unit test tests. And you can actually run vanilla Python unit test tests under Marbles and get the Marbles failure message without changing your code. The fourth library on this list is Nose. Nose is no longer being maintained. I also believe that Nose does not itself have tests, and you should not use Nose. The reason I'm listing it here is that you will likely hear about Nose at some point from someone. It used to be very heavily used. My first unit tests were written in Nose. I wish that it was better maintained, and I wish it was something that I could recommend to you all to use, because they are incredibly, incredibly simple, and it's a good way to get started. But steer clear of projects that are not maintained. Steer clear of projects that are not themselves tested. This last one is not a unit testing library per se, but it is in the Python testing family of libraries, and it's a really cool library called DocTest. This is also built into the Python standard library. I'm not sure if it was always part of the standard library, but it is now part of the standard And so what it does is it will look into, who here is familiar with a doc string? Cool. So for those of you that are not familiar with a doc string, a doc string is this triple quoted line here. It's basically a string annotation of a function or a class that describes what it does. It can describe what parameters it accepts. It can provide what types of things it returns, things like that. And so what doc test will do, so I can write a whole bunch of things in here. So I could say, like, I could add this to my doc string and say, like, look, here's an example, here's some like example usage. Right? And so what doc test will do is it will look inside your doc strings, and it will look for things that look like an interactive Python interpreter. Right? And what it will do is it will execute those commands and make sure that it actually gets exactly what's shown in your documentation. So basically, it will sort of reach into your doc strings, find some example code, run that example code, and make sure that your documentation examples actually like show the correct behavior, like show the behavior that's actually happening, which is pretty cool. You probably don't need to worry about it, but it is there for you. If you ever are like, oh my god, my doc string examples are getting so out of date, there's a tool for you. Okay, so am I correct in assuming that most of you all do most of your development in Jupyter Notebooks? No? Yes? Some yeses and some nos. Okay, so we're going to cover both. I'm going to start with Jupyter Notebooks just to make sure that we have time to cover it. I mean, it's important that we cover both, but I want to make sure that we spend a good amount of time here. So the first thing is that if you want to test your code, the best thing you can do for your code is actually to get out of a Jupyter Notebook, get it into a package, test it there, and then import it into your Jupyter Notebook. And the reason that I really encourage you to do that is that we really want our tests to be reproducible, right? So if we run them multiple times in a row, we want to get the same result. And it's really easy to kind of mess up the state of your Jupyter Notebooks because of how Jupyter Notebooks sort of manage the global state. And you can do this by running cells out of order, or deleting cells without explicitly deleting the objects that were defined in those cells, and stuff like that. And so it's kind of tricky to make sure that you have like a clean, isolated, identical environment like inside a Jupyter Notebook, and we sort of want that clean, isolated, identical environment for our unit tests. But refactoring code into packages takes time. And we can make some progress on testing our Jupyter Notebooks even if it's not perfect and even if we're not factoring our code out. So the first thing that we can do is we can execute all the cells in our notebook and ensure that none of them raise an exception. This is not really anything extravagant. It, of course, doesn't give us any guarantees that all our cells are doing what we think they're doing. But if you've ever had, a notebook laying around and then, you return to it a couple weeks later and you try to run it and it just doesn't work anymore, that can be kind of frustrating. So I linked to an example of how to write a test that just executes your notebook and looks at the output of every cell and makes sure that there's not an exception. So this is sort of the bare minimum that you might want to do. The other thing you can do is that you can actually add tests to your notebook itself. So, for example, let's say you define some functions at the top of your notebook. You can add a cell right below that defines unit tests, and then you can run those unit tests right there. So there's a couple of caveats. Running unit tests inside a Jupyter notebook is different than the way we ran them on the command line. That if any of you want to take this route, we can sort of dig into it individually. But I added a note about what you have to do differently and like why you have to do it that way. The thing to bear in mind if you're adding unit tests like directly into your notebook is that you have to be really careful about cleaning up after yourself in between test runs. So in Jupyter, like the results of every evaluation are stored in the global state unless they're explicitly deleted with the delete command. And so this means that if you rename a test or if you remove a test from your test method and like rerun your notebook, unit test is still going to find those old tests and it's still going to try to run them. And like it gets, and then you're like, why am I seeing test failures for tests that like I don't see in my notebook anymore? And it can get really, really confusing. And so, if possible, what you should try to do is either restart the kernel in between test runs, or the last library that we're going to talk about for testing Jupyter notebooks is called IPyTest, and it actually has a function for cleaning up anything that looks like tests before you run your tests. Another tool that you can use, this is a library. It's called nbval, and it's a PyTest plugin that validates a Jupyter notebook basically against itself. And so the way it does this, you know how Jupyter notebooks like checkpoint themselves every so often? So basically what this does is it will execute every single cell of your notebook, and it will make sure that the output of every cell matches what's in the saved notebook. So it uses the saved notebook as sort of like the test criteria. And so this can be a pretty good way of ensuring that your notebook is doing exactly what it did last week. But again, if your notebook is producing different results on purpose in between runs, like this is obviously going to complain about that. And then the last one, which I think is the most promising one, is IPyTest. And so IPyTest allows you to run PyTest unit tests inside of Jupyter notebooks, and they address some of these concerns of testing in Jupyter notebooks, specifically these things about how do you clean up your state, how do I find tests, and things like that. So they used to support unit test tests, but unit test support has been deprecated, and so they only support PyTest tests. So I'll just remind you all again, I do not care what library you use, as long as you're writing tests. I wish that I was a PyTest user so that I could, for those of you that want to be using IPyTest, so that I could like really be there with you in the trenches, but unfortunately I'm not. But I just want to sort of show you the example notebook that IPyTest provides to sort of see how, and this is linked in the docs, but just so you can see how this works. So the first thing you do, obviously, is you import PyTest and you import IPyTest. In order to be able to import them into your notebook, they need to be installed in the environment that you're running your notebook from. So this might be a conda install, this might be a pip install. And then, so here, they're defining one very simple function at the top of their notebook that basically returns X. Am I reading that right? Who knows what this function does? Oh, just floor division and then multiplication. Okay. Look at that. It's very easy to tell what this function does by looking at the tests. This is what people mean when they say the test should be documentation of your code. Okay, so then they have a cell where they define all of their tests, and then they run them all with ipytest.run.
Second group showing.
This part?
Yeah.
So this is what's called a. Okay. So there's a couple things going on here. Basically, what this is doing is it's saying, I want to run my test over every single one of these combinations, but I don't want to write all of this. I don't want to write separate tests for each of those combinations. I just want you to iterate over all of them. So this pytest mark.parameterize is what's called a pytest fixture, which this is one of the reasons that I don't like pytest. I don't like pytest fixtures. I think they're very, very confusing. But you could look into the docs for what, for like how the parameterization fixture works. But that's basically what this is doing. It's just saying, like, I want you to run this assertion for every combination in that list. Does anybody have other thoughts on how you might test a Jupyter notebook? Okay, just curious. So, testing packages. And again, I'm going to sort of run through this, and then we're all going to get like hands-on experience actually writing them, which is going to be the best way that this is going to get into your head. So if you're worried that I'm going a little bit fast, don't worry, you'll have a chance to internalize all of this information. For those of you that are not primarily working in Jupyter notebooks, but you are writing, you're writing actual packages in libraries, there's this question of like, where should my tests sort of go? So let's say that we have, I have a very simple package with this structure. It has two modules, foo and bar. And I want to test the code in foo and bar. And there's a couple of different places that I could actually put my test code. The first option is that I could actually put my tests directly in my modules. I could put my tests in test files next to my modules. This is sort of what we looked at with nums and testnums.py. They were right next to each other. Or I could put my tests in a completely separate directory of my project. And I sort of want to talk through each of these different places and the sort of pros and cons of each. So, putting your tests actually in the source code file. The pro that I hear for this is that it helps you remember when you're changing code to update the tests because they're right there in the same file. But it's generally it's really not a good idea to put your tests in the same file as your source code. And the reason that we don't want to do this is because you would then have to find a way of communicating to whoever is importing your module, like, what are the actual functions that I intend for you to use, and what are the test functions that I don't intend for you to use? And because when they import their module, they're going to get everything. They're going to get your code, and they're also going to get your test code. And you would have to do lots of gymnastics to hide the test code from them. So it's just like generally not a really good idea. The same thing kind of applies to putting test code in files next to your modules. So we still have this problem of, if someone imports my package, they could say, like, from my package import test foo, and like we don't really want to do, like, they don't care, they don't need our tests. Like, I need to be able to import my tests because I need to be able to run them, but like this is not really something that we sort of want to expose to a user. And so it's generally considered best practice to put your tests into a separate tests directory at the top level of your package. And to help you keep things organized, you can have that test directory have the same structure as your package directory. So if there was nesting, we would have like the same levels of nesting in our test directory. So that it's very easy when you're sort of looking at a tree of your project. This diagram is called a tree, by the way. Macs do not come with the tree command, but you can install it. It's very helpful. It works like this. Very helpful. It's better than, I prefer to LS because it will show you sort of all the levels of nesting. I did not finish that sentence, and I apologize. So generally, we want to put them in a separate directory that has the same sort of structure as the package that we're testing. And the disadvantage, which I did not complete here, and I will complete it after the seminar today, is that you miss out on the visual signal when you're changing code that you need to also update the test. But the more practice you get writing tests and the more practice you get running tests, it's really not going to be something that you forget to do. You will very quickly, if you are diligent about writing tests, you will very quickly get into the habit of running tests very frequently when you're making changes to code. And so if you forget to update some tests after a change that you made, you're going to be notified pretty quickly if you need to sort of update some tests anywhere. I find, do any of you sort of compulsively save documents that you're working on? Like press like Command S all the time? Yeah, that's how I feel about like running unit tests. It's like that compulsive of a thing when I'm doing it. Okay, so let's assume we got some tests written. How do we run them? So again, I'm going to talk about how to run unit test tests. The PyTest talks will be able to tell you how to run the PyTest test. So unit tests can find and run all of your tests as long as you follow a couple of conventions. The first is that your test files should all be modules or packages that can be imported from the top level of your package. So this means that they need to be Python files. They need to be organized into a package structure. They need to have init.py files. I don't know if you are familiar with init.py files or if you covered them in the previous sessions. Yes, no, maybe. For now, just like toss an init.py file in your test directory and you'll be good to go. Everything has to start with, except for your test case names, everything has to start with test underscore. So this means that your test files have to start with test underscore, and your test methods also have to start with test underscore. If it starts with anything else, unit test is going to be like, oh, you're not a test, I'm not going to run you. If you create something that starts with test underscore that's not a test, unit test is going to think it's a test and it's going to try to run it, and like some weird things might happen. If you want to use a different pattern, I think you can provide a different pattern for unit tests. Like if I wanted to say all of my tests start with like JSA test underscore, I think there's a way of doing that, but it's better just to stick to the test underscore convention. So assuming that you've sort of named everything with test underscore and that it's all importable, you can actually run all of your tests just with this command. So the unit test discover command is going to search for anything named like a test. It's going to collect it all, and it's going to run every single one of them, and then show you all of the results. You can also run tests individually. So let's say that I just wanted to run the tests for my foo module, or I just wanted to run this one specific test case in my foo tests, or even one specific test method. That is also possible. Another way to run, so this is how unit test discovery works. And this is one way of running unit test tests. The other way is the way that we did earlier, where we just pass our test file straight to the Python interpreter. So we gave it, I apologize, that dash M should not be there. But what we just did is that's all we did, right? So we're just passing the file straight to the Python interpreter. In order to get that to work, we have to add this little code block at the very bottom of our file. And so basically what this tells Python is like, hey, like if I just got passed straight to the interpreter, if name equals main is like a really fancy way of saying like, did I just get passed straight to the interpreter? Run unit test's main function, and unit test's main function is going to collect all the tests and run all the tests and spit out all the results. If you don't have this block at the bottom of your file, and you just try to run it, let's see what happens. I'm going to take out nothing happens. So basically all it did was like, I opened this file, I defined the class, I closed the file. Okay, we're getting close to actual test running time. So at a certain point, you'll probably have quite a few tests on your hands, and setting them up. So like importing your code and like setting up the combinations that you want to test and whatever. And that setup can actually get pretty repetitive, especially if you need this sort of same artifacts around. You're passing them to like lots of different tests. And if you find yourself in this situation, you can factor your test setup code into a method on your test case called the setup method. So basically what you're saying is, before I run every test, I want unit test to run this setup code. It could be loading test data from a file. It could be creating like an object that you want to test. It could like anything can really go into your setup method. And unit test will automatically call this setup before it runs every single test. Because what it wants to do is it wants to make sure that every single one of your tests is running in a completely isolated, pure environment from all of your other tests. So the counterpart to the setup method is the teardown method, which is run after every single unit test is run, unless an exception is raised, which is an important thing to keep in mind. So a teardown is if you need to do any additional cleanup after your test to make sure that it doesn't sort of bleed into other tests, you would use the teardown method. I generally, just to be safe, if I'm creating objects in setup, I always delete them in teardown. Even though they're going to get recreated for the next test because that setup method is going to run again, I delete them in my teardown just to be extra sure. So for a little bit of lingo, the environment that's created in between setup and teardown is what's called a test fixture. So when people talk about PyTest versions of PyTest's version of fixtures is very different. Because PyTest tests are not organized into classes, you can't, fixtures are defined, fixtures have to be defined sort of elsewhere and attached onto your PyTest tests by what are called decorators. It's all complicated. In unit tests, because we're organizing all of our test methods onto a class, we can define the fixture at the top of that class. So generally, the way I like to organize my test cases is I like to create so I've got this set up. I'm setting up a testing environment. Generally, what I like to do is I like to group my tests into tests that require the same setup. And so, I will basically say, okay, this is my test case for condition X, and I'll set up condition X. And I'll have all my tests that do various things that should happen in condition X. And I'll have a separate test that sets up condition Y, runs all the tests for things that should happen in condition Y. And that's generally how I like to sort of separate my test cases. But again, for smaller projects, it's totally fine to have just like a single test file, to have a single test case with, like one test case per module. Like that's totally a legitimate way of organizing your test code. You will know you will know when the moment is right for you to start splitting your tests up into separate test cases and into separate test files. And at the end of the day, you should be organizing it in whatever way makes it easiest for you to understand what they're doing. I asked you all to bring or to have on hand a Jupyter notebook or or some code that you're working on that you can write some tests for. If you don't have that, we can get some example code for you to work on. But what I want to do for 3:45, what I want to do for the next half hour is give you all just an opportunity to individually work on writing, even if it's just one unit test, like writing a test for some piece of your own code. Again, the only way that you're going to get good at this is by practicing. It is painful to start, but you get the hang of it really, really quickly as long as you keep doing it. How does that sound? Before we split up, what questions do you have?
Don't write in Python.
Oh boy. What do you work in?
R.
I'm sure there are some unit testing libraries for R.
Some of the packaging tools for R will come in with pre-built in tests to run on the documentation and all the functions that you just have to provide an example.
So I want you to write tests for your own code.
No, so this one will execute everything. So it goes through your own code in the package, runs it with the example data that you give it.
Oh, interesting.
And it'll validate the package for you. It'll test the package for you.
What is it?
I don't remember. It's been a while since I took these classes.
Okay. Oh, and let me put a pin. We can talk after we sort of all split up. Is there any documentation that you all want me to have up on the screen while you're working? I can also show you. I showed you how to run the docs, these class materials locally, so you can sort of jump around on your own. Would that be valuable for everyone to do? To have it running on your machine? Okay. So in order to get this to work, you do have to have, you need Sphinx. You need to have Sphinx installed. So if you didn't get so if you were able to install from the requirements.txt file, if you were able to install all those requirements into an environment, you should be fine. Was there anyone who wasn't able to get the dependencies installed? Okay. So in order to, let's go back to the repository. So what we're going to do is we're just going to copy these two commands at the very end of the README for this repository. The first is going to build, it's going to let Sphinx build the docs into HTML. And then the second command is actually just going to serve that HTML on port 8000 on your local host. So I don't know if you all were listening, but these class materials are just written using restructured text, which is kind of like Markdown. And Sphinx is a really amazing tool for taking restructured text and turning it into HTML. So what you're going to do is in the top level of the repository, you're going to want to run Sphinx build. You're going to want to run this command, which is in the README, so you can just copy it from there. How did that go for folks? And then the second command is just going to serve that HTML on a port of my choosing. The reason this command is in parentheses. So a parentheses indicates that I want to run this command in a subshell. I don't know a ton about subshells, but I do know that a subshell will sort of execute everything inside of it, and then it will return you to the working directory that you were in wherever you called it from. And so if I'm executing a command that changes directories, I usually toss it inside a subshell just because I find that more convenient. So what we can do after we build the docs is we can cd into the build directory and serve the docs on port 8000. And then if I just go to this URL, there are the docs. This is actually how I'm already serving the docs for this right now. Who was able to do that? Cool. Cool. All right. So let's break for unit test writing. If you need my help with anything, please just holler. My name is Jane, by the way. Did I say that? I did say that. I did say that at the beginning. So if you either haven't yet got the docs pulled up to navigate through, if you don't have anything that you want to write tests for, just raise your hand. Yes?
I might need some test code. I don't use Python or R.
You don't use Python or R.
No, I program robotics here.
Okay. It is now almost 20 after 4, so we've got about 40 more minutes together. So I will just want to sort of regroup. Are you on your way out?
Yeah.
That's okay.
Thank you very much.
Yeah, of course. You have the materials, they're not going to go away, so if you want to read through what you didn't get through, they're available for you. Yeah.
I do have some questions. Like, I'm currently writing like a module involves like user input. So, do you write tests regarding to like if they input something you're not expecting? Like,
Yeah. So this.
it's complicated.
Yeah, it is kind of complicated. So I think what you've touched on, and this is what. So I want to sort of talk about the tests that you all wrote in the last like half hour, what you sort of found, what you sort of thought. We can start here for sure. So I think what you're describing is exactly what we mean when we say like writing unit tests make you think about ways that people might interact with your code that you haven't thought about before and that you haven't like considered. And so I think in this case, probably what you want to do is, I don't think you want to, so I think the first thing that you want to do is add some logic to your code that handles like unexpected inputs. And so like, let's say that it expects like a string. Or what does it actually expect? Let's start. It expects a string. So what you can do in your code,
I guess I can like sort of guide them into like a format that makes sense.
well, so where did I'm going to show you sort of what I'm talking about. So what I think you should do is you want to actually handle handle the inputs. So one way you might do this So these functions expect to receive an integer. So one thing I could do is I can add this to like the very beginning of my. This is a technique called like, I think people call this like input validation. But you know, if you think there's a chance that people are going to be passing all sorts of different types of things, and you only support one, this is a really good idea. Checking to make sure that the thing you got is the thing you can actually work with, and raising a type error if it's not the right type, is a good thing to do. And then what we can do in our test file is we can say, we can add this assertion to our test, which basically says, make sure that if somebody passes something that's not a string, or sorry, that's not an integer, a type error gets raised. Does that make sense? So let's try to run that. Let's see if I actually did that correctly. Live coding is always an adventure. There we go. Okay. Let me just explain what just happened. So assert raises is a special assertion method in unit test that wants you to call it in a context manager instead of just call it as a method. The context manager is this with syntax in Python. But if you look at the docs for assert raises, you'll be able to see like how you're supposed to call it. But basically, what you do is you say with self.assert raises, you provide the exception that you're expecting to get. And then inside your context, you say, okay, this is the code that I want you to execute that I think should raise a type error. I thought that it would work like this. I'm actually kind of surprised that it didn't, but anyway. So that's something that you could do. So I don't think you want to test. I don't think that you want to test that the input is what you think it is. I think what you want to do is you want your actual code to validate that the input is the right type, and add a test that your code does the right thing when it gets input of the wrong kind. Does that make sense? Okay, cool. All right. Does someone else want to talk about a test that they wrote or a problem that they encountered?
Basically, for each module, you want to write a new test file, like test.py, right?
That's how I do it. Yeah. Yeah. And I like to put them in their own tests directory.
It doesn't matter like where the test directory is. In my I'm using this like cookie cutter.
Yeah.
That like generates the structure.
Yeah.
So it's slightly different from this. It's like the test files are with the tests directory is actually within my package. So I guess as long as it knows where to find it.
Yeah, I wonder why they made that cookie cutter like that. That's like totally viable.
Okay.
The only reason I don't do that is because I don't want someone importing my package to like accidentally import my text, because they don't need them. So I keep them entirely out of my package.
So they have a an option to do this.
In cookie cutter?
No. Like for people to import your packages, they have an option to not import tests.
Well, so if they say like from my package import star, they're not going to get my tests in this scenario. because my tests are in a completely different directory. Does that make sense?
Yeah.
If my tests were in here,
Yeah, that's my case. Like it's within that my package.
yeah. I mean, you'll be able to run your tests, and it's probably not a big deal, like because someone would have to know that your tests were there in order to import them. Like, it's probably not a huge deal. I just prefer to put them at the top level, like for that reason.
Okay.
Was someone able to write a like functioning unit test?
There was
Okay, you're gonna have to tell me about it because you're both too quiet.
So, something I frequently encounter is that SciPy has like weird parameterizations for their statistical distributions. And so I usually write these like small functions to reparameterize based on like whatever I actually want to use.
Yeah.
So I went in one of my notebooks and wrote a unit test, and basically what it does, so my parameterization that I want to use is like mean and standard deviation, and then the function converts that into the parameterization for the SciPy distribution. So I put in the mean standard distribution or standard deviation, and then I define the distribution and then pull off the mean and standard deviation from the distribution and do a assert almost equals
Okay.
the two to make sure it like gets back the parameters that I started with.
That's brilliant. That's a brilliant unit test. Good work. What about you?
So I'm mining some ontology database, and so I don't need the whole database. I just need specific files from the database. So I just found it easier to load each file as its own object class. So, but I want to be able to filter data within these objects. Generic function where you specify the class object, whatever attribute they want. And then it'll return true or false for the attributes. So just wrote some dummy class test functions, tested that dummy class, and see whatever. Give them some dummy data that has those values.
Yeah. Cool. Also a great unit test.
I have a question on that. For example, because maybe my program working with, for example, with just object detection. So for example, I'm trying to understand like how you can build a unit test on that. Because for example, you have in the picture you have a circle. What I program to is you click the circle and then they draw the contour on it. But like how you design a test on this, because sometimes you don't even know the like if the program didn't provide a force contour, you couldn't even tell it's force.
Yeah. Yeah. So I think that so you're thinking about what your program does as sort of like the highest level possible. And when you're writing unit tests, you want to be thinking about your code at the lowest level possible. So so I'm sure that there's a ton of code that goes into detecting those clicks and drawing those contours.
Yeah.
And each individual part of that is something that you can potentially test to make sure it's working correctly. So it could be the thing that it could be the part of the code that registers that a click occurred. You could find a way of testing that. Maybe I'm like struggling to think about all of the machinery involved in such what seems to be a complicated task. But when you're writing unit tests, you do want to be thinking at this like very, 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 very low level of your code, and trying to break up your code into the discrete steps that it's performing and testing each of those steps independently. Because the idea is that if you can assert that every single one of those steps did what it was supposed to, you get some, not perfect guarantees that the whole program is working the way it's supposed to, but, it's better than nothing. Okay, so we have about half an hour left, so we're not going to be able to cover everything else I wrote down, so you are going to just have to read through it on your own So I apologize for that. But what I do want to talk about in the remainder of our time together, I want to talk about test planning. I want to talk about test coverage. So these two, both test planning and test coverage, are sort of getting at this question of like, what tests should I write? Like, what tests do I need? And as I said to a couple of you, as I was sort of moving around the room, is like, this is actually the hard part of unit testing. This is also the really creative part of unit testing. This is also the really fun part of unit testing. So test planning is the process of determining like what conditions and functionality you're going to test for. And so when you sit down to actually write tests for your code, like, you might find that some of the tests that you planned to write you don't actually need. You might find that you forgot to include some tests in your test plan. Like, that's totally fine. It doesn't matter. Your test plan is not like set in stone. And depending on what kind of environment you're writing code in, you might write this test plan down on paper and you might send it to someone to review, or you might never write it down on paper and it might just be something that lives in your head. The point is that as long as you're thinking about what tests you need, you're doing test planning. And so as you get more experience writing tests, your test plans, like the things that you think to test for, and also your tests are going to start to look different. And so when you're starting out, it's best for you to sort of focus on trying to test as completely as possible, like the conditions and the functionality that you expect your code to be sort of operating in. And sort of don't worry too much about like, oh, you know, I'm repeating myself a lot in my tests, you know, I'm not writing dry test code. Don't worry about that up front. It's better to get a lot of practice writing way, way, way too many tests, because you'll learn this test planning habit really well that way. So how do you sort of go about test planning? So I have a couple of questions that I generally ask myself to sort of cue myself up and get me thinking in like a test planning mode. The first I call bread and butter. These are also called the happy path. These are the obvious things about your code that just like have to work. Under normal conditions, normal behavior, an add function should take 2 and 2 and return 4. A good place to look for these sort of bread and butter testing opportunities is in the name of whatever you're testing or in the docstring of whatever you're testing. So for example, our isEven function, the docstring said like return true if n is even, otherwise return false. And so there's 2 unit tests for me right there. Like straight out of the bat. I know that I need to test for those things. I gotta make sure that those things are working correctly. Another good place to look for these sort of happy path or like bread and butter tests that I think is probably going to be less applicable to this group is in like a requirements spec or in like acceptance criteria from a user. If you're mostly writing code for yourself, you probably don't have this, but like if you have a consumer that's like, I want this feature, I want it to perform this way when I do this action, and I want it to perform that way when I do that action, those are really great places to start test planning from, because like the answer is basically right there for you. Another one that we have been talking about already is edge cases. So if there are edge cases that require special handling in your code, these are really, really important to test to make sure that they're working correctly. Again, when we're writing code, we're mostly thinking about how the code works. We're not thinking about how the code doesn't work. And so it's really easy to miss these edge cases. So when I was first writing the examples for this seminar, I completely wasn't even thinking about like 0 and 1. And the fact that I needed to start my range at like 2. And so I got that 0 division error when I was first writing this, and I was like, I need to handle 0 and 1 especially. So a good place, so you can sort of ask yourself this question, are there any edge cases that I need to handle specifically in my code? And a good place to look for existing edge cases that are already being handled, like especially in your code, is in if statements. They can sort of lurk in there. And if there aren't, so even if you sort of look through your if statements and you're like, all right, there aren't really any edge cases in my code that I need to test for right now, it's still valuable to think through, okay, are there any edge cases that are not currently being handled that I need to handle, and then that I need to make sure that I have tests for to make sure that they're being handled correctly. So if you're in that scenario, so like you're looking at your code, you're in your test planning mode, and you're like, oh my god, like there's this edge case that I'm not handling, and I need to handle it. Your example is like, what if the user puts in a non-string? It's a good idea to add so you say, okay, when that happens, I want my code to do X, Y, Z. I want my code to raise a type error. What you should do, and what I want you to try to practice doing is writing the test first. So writing the test that says, okay, when my code gets a non-string, it should raise a type error. So write that test, then go change your code, and then you'll know that you've successfully handled that edge case once your test starts passing. This is a kind of glimmer of a technique called test-driven development, which you may or may not have heard of. But test-driven development refers to a coding workflow in which you write your tests before you write any code. And so you write a bunch of failing tests, and then as you implement the code according to what the tests expect, they start passing. And once they're all passing, you know that you've sort of fully implemented what you were expected to implement. I don't do full test-driven development. I don't think I actually know anybody that does full test-driven development. And I think you will only make yourselves miserable by trying to do full test-driven development at this point, simply because thinking about tests before you've written any code is a pretty advanced thing to try to do. So don't try to go full TDD. You're going to be really sad. And you're going to end up not only iterating a lot on your code, but also iterating a lot on your test code, and that is all takes a lot of time. But if you do think of an edge case that you need to handle, you can sort of get in this sort of practice of writing your tests first, and then seeing how that can help you know when you've actually implemented the thing correctly. Another one, of course, is thinking about failure mode. So what kinds of inputs would cause your code to break? Or what kind of situation would cause your code to break? So a really good example is if you have a recursive function, what types of inputs would cause you to run into a recursion maximum depth error? And so there are other, code can break for other reasons as well. No, that's okay. You're getting us at the very end. You missed it all.
That's the recording.
So code can break for a lot of other reasons, not just bad inputs. One thing that we also mentioned earlier is that if your code relies on a database connection, what happens if that database is not available? What happens if you can't connect? What about if your code makes a query and that query returns 0 records? What does your code do in that scenario? And so when you're trying to think through sort of all of the sort of conditions that might trip your code up, either that might trip your code up explicitly, where some exceptions are being raised all over the place, or failure modes that are sort of more silent. And not all of these failure modes are going to make it into tests in your test plan. They might make it into special handling in your code. They might make it into tests. They might just be something that you document for the user to be like, hey, yeah, I just can't run on Windows. Sorry. Or I just can't run on Python 2, something like that. So you don't necessarily want to write tests for the behavior of your code in Python 2. You just want to say look, it doesn't work with Python 2. Don't use it. So another way of of thinking about how, like what tests do you need, like what tests should you have in place, is a metric called test coverage. So just for the Jupyter Notebook users in the room, we do not have a version of test coverage for you. This is exclusively for Python packages and libraries. We can produce this metric called test coverage. And so test coverage basically tells you what percentage of lines of code in your code base are exercised when you run your tests. And so it's not a perfect measure because there's no guarantee that executing a line of code when your tests run means that you're like actually testing anything about what that line of code does. But it can help you identify areas of your code base that aren't being tested at all. So it can sort of give you the lower bound? Upper bound? Lower bound. It gives you the upper bound of what you're testing. Yeah. It gives you the upper bound of what you're testing. And so we can get a coverage. There's this, the package is called coverage. It's a really useful Python package, and you can run it straight from the command line like this. In this situation, remember we had our test file right next to our module, and so I tell coverage to emit the test file because I don't need coverage for the test file because it's my test file, so it's clearly going to be 100% because every line of my test file is going to get executed when my tests are executed. And so I can get a report that tells me, okay, like 91% of my nums module is being covered by the tests that I have. And I can say, okay, like I'm missing 2 statements, and I want to see what those are. So I'm going to go over here, and I'm going to run coverage. The reason my coverage is, I bet if you all run these, your coverage will be 100% because I asked you all to test cases for the statements that I do not test for. But what you can do is look at coverage, look at an HTML report of the coverage. This is my favorite part of the coverage module, by the way, is the fact that you can get like an HTML report of your coverage that you can like click into, and you can see exactly like what's not tested. This is like so helpful. Okay, so looking at this HTML report, I can see, yeah, like I'm completely missing these special lines for, or like these special branches for 0 and 1 are neither composite nor prime. And so if I go back into my I'm going to leave that there. If I add I'm going to make sure that for both of these cases, zero and 1 are neither composite nor prime. I'm going to run coverage again. Now I'm running 6 tests instead of 4, and my coverage is at 100%. So 100% test coverage is really satisfying. It's really natural to try to get to 100% test coverage, but this is also this is a trap, and it's a very satisfying trap into which you can wind up sinking many, many hours that are probably better spent elsewhere. So the reason I say it's a trap is that it's possible to get 100% test coverage and not be testing the important behaviors of your code at all. Like, I've seen that happen I've seen that happen before. Again, it's an upper bound. It doesn't necessarily guarantee that anything other than the fact that that line of code was executed when your tests were running. It doesn't tell you that it's actually being tested well, or if all the right edge cases are being tested, or that all the happy paths are being tested. It doesn't tell you any of that. And also, you know, spending a lot of time testing every last line of code, just to get like 100% test coverage. Like, if you're quick at it, go for it. Like, get that 100%. But if testing every last line of code is actually a considerable time sink for you, you gotta like use your head and think through like, okay, you know, is this worth testing? You know, sometimes you have code that is so dead simple that like testing it would just be like, I don't know, an exercise for you to do on your own time if you really like felt that you needed to do it. But like, the sort of integrity of your code base is not going to suffer if you don't test for that thing. You should put more stock in your test plan. So thinking through what tests you need, thinking through edge cases, thinking through failure modes, than in your coverage metric. And you should use your coverage metric to identify. You should really use your coverage metric to say, okay, is there anything in my test plan that I missed? But I'm a huge culprit or offender of like spending way too long to get to 100% test coverage. So I feel for those of you in the room that are susceptible to this type of gratification.
What is the average like coverage?
Oh God.
In real life.
Well, so this is really hard to determine, right?
Yeah.
Like, how could you run coverage across every code base in the world? I also don't think I'm allowed to tell you what it is at 2 Sigma. It's not what you think. It's not 100%. Even though, like, a lot of, so I guess a sort of a corollary to this is that you might find yourself in a situation where there's a policy that says every line of code has to be tested. And
For something to be like published?
yeah, it depends on the team, it depends on the company, you know, just like different places have different, you know, different policies, different practices. I would not encourage any of you to adopt that for yourself. I would not give yourself a 100% test coverage, like a 100% line coverage goal, because I want you to like use your head. I want you to actually be thinking about what your code does, like not like the lines of code that it has. And again, you know, it's possible to get 100% test coverage without, you know, you could get 100% test coverage and only test for like one scenario. And it's much better to think through, okay, what are the 3 scenarios that I need my code to work in? And, you know, that's not going to move your test coverage, but it's where you should be focusing your time. Okay, so we have like 10 minutes left. So I'm not going to go over the sort of testing best practices and anti-patterns, and also untitled code. You can read through these yourself. There's links to some really great catalogs of testing anti-patterns. As you get more practice writing unit tests, you'll probably find yourself doing some of these anti-patterns, and if you have them in the back of your head, and you can sort of notice when you're doing them, you'll be like, oh, I'm doing that thing that I'm not supposed to do. But don't worry about it. Don't worry about it too much. It's more important that you're writing unit tests than that they're like perfectly designed and like perfectly built unit tests. So before we break, I do want to talk a little bit about testing stochastic programs, and also what a workflow for what a unit test workflow for a researcher might look like. So I mentioned this earlier, but unit testing doesn't really translate well to stochastic programs. So a stochastic program is a program where if you run it multiple times, you get slightly different results, or maybe not slightly, but you get different results on different runs of the program. So it's not deterministic. And unit testing assumes that your code behaves in a deterministic manner. It sort of relies on that. And so, that being said, there are still a couple of things that we can do to test stochastic programs. The first thing that we can do is if you have an expectation about the distribution of your results, you can run your program a bunch of times, collect all of the results, and then have a test that looks at all those results and makes sure that it matches your expectation. I do this a lot. I leverage this quite a lot. And so this doesn't necessarily mean, so if your test fails, that doesn't necessarily mean that there's anything wrong with your program, right? It doesn't guarantee that something broke somewhere. But that failing test is a good sort of motivator for you to go look at those results. Say, okay, my test, these are outside of the expected distribution, what happened? And you can go look at the results, and you can sort of make a call about whether or not they look reasonable. It just sort of depends on the situation you're in, but I don't know if you're able to look at every single result of every single run of your program. So it's helpful to have something in place to sort of pick out a subset of those results that you might need to give a little bit of special attention to. The second thing that we can do, and we sort of talked about this a little bit before, is, in many stochastic programs, there's a lot of setup that needs to happen before entropy even enters your program, right? So even though overall your program is stochastic, there are many, many, many deterministic parts of your program. And you can, and because they're deterministic, it's possible to test those things. And we really want to test those things because as we iterate on our model and as we iterate on our input data, we want to make sure that any changes that we see in our results are isolated to those changes that we're making to the data or to our model. And that, again, it's not some weird behavior of our code that's messing with our results. So let's say we have like a stochastic program. It has a lot of deterministic setup code to it. What might it look like for me to sort of incorporate unit testing into like a Jupyter Notebook first sort of workflow? So I would start by prototyping my code in a Jupyter Notebook. This would be all the setup involved, so like reading all the data, transforming all the data, and it would also be setting up the actual model, executing the model, and outputting the results or something like that. And in this stage, I would not be thinking about testing. I would just be thinking about getting my model set up, and I would be thinking about what my model's outputs should look like. And once I've got like a model in my Jupyter Notebook, I think it's what I want. Then I would add tests I would add those types of tests for the distribution of outputs. So I would say, okay, like I think that my results should conform to this distribution. I'm going to write a test that will run my notebook a bunch of times, collect all the results, and make sure that those results seem like they're drawn from that distribution. And sorry, I have to go really fast because we're running out of time. But there are links in here to ways that you can execute Jupyter Notebooks from Python. So you could create a test file that executes your Jupyter Notebook maybe like 100 times or something like that, and then runs your tests. You could do something like that, all within one file. The next thing that I would do is I missed a number. I'm sorry. The next thing that I do is I would factor out all my setup code, all that deterministic setup code, into a reusable package, and I would test all of that deterministic setup sort of outside of my Jupyter Notebook. And after that, I would replace that setup code in my notebook just by importing this package that I created, and I would run my distribution tests. And so the reason I want to do that in this order is that I want to do two before I sort of factor out my setup code, because I want to make sure that when I factor it out, I'm not dramatically changing the distribution of results that my code is producing. Does that make sense? It has like the flavor of test-driven development, And it kind of has the flavor of like detecting regressions, right? So a regression is, code that used to be working that's no longer working. We can say, okay, our model is producing results that conform to this distribution. I factored out all my setup into a package, and I'm just importing that package now. Do my results still conform to that distribution? And so at that point, you're like in pretty good shape. I would give you like a gold star. I would definitely give you a gold star for getting to that point. Now, looking forward, sort of what does your workflow look like? So when you update your package, so we factored out our set of code into a reusable package. At some point, we're going to need to change something about that package for some reason, because we always have to change code. No code stays the same forever unless nobody's using it. And so what I want you to try to do is, again, don't obsess about test-driven development, but try to write tests for the thing you're changing before you actually change the thing. It's a helpful signal that you've successfully implemented the thing that you wanted to implement when that test starts passing. So also when you update your package, you should run the package's tests as well as the distribution tests. So update your package, make sure that all of the package's tests run, and also make sure that when you run your notebook with this updated version of your package, that your results are still in the distribution that you expect. Same thing when you upgrade dependencies. Maybe you depend on pandas, maybe you depend on SciPy. When you upgrade dependencies, run your package tests, run your distribution tests. They're probably going to be the exact same. It's a really good habit to get in, and you might uncover some syntax errors or some deprecation warnings that you can then go and fix in your code. And then just periodically, I would run your distribution tests. I have tests set up. I have lots of distribution tests set up just for data, like raw data sets, where I'm like, I expect this column to be distributed this way, and like, I just have those tests running. Every time I get new data, those tests run. And so if any file looks weird, I get pinged by a test failure, and I can sort of go look at it. So periodically running your distribution tests is a good way of sort of keeping an eye on, is my notebook doing roughly what it was doing like 3 months ago? All right. I'm going to stop talking. What questions do you have for me, if any? No. I linked to this GitHub repository in the course website. Again, that repository just has all of these written materials in it. We all were able to build and serve the docs locally, which is cool. So I would encourage you to read through. Unit 2, Lesson 1, and also read through Lesson 3, since we had to go through that kind of fast. And there are some links in there to some specific things that we talked about if you want to read more. And then the very last page just has some links to documentation for some of the tools and libraries that we talked about today, and also some links to further reading on some of the topics that we discussed. And also this last link is a link to my talk on unit testing for data, which I know is relevant to at least one person in the room. Cool. Thank you all.
Thank you.